Hi, everybody, and thanks for coming. I'm here today to tell you a little bit about a passion project of mine that I hope to take on some new life with new friends, and we can see what we can do with this. It's an opportunity to use TensorFlow models in your next Flink program. Let's start with asking the question: who knows about TensorFlow? Yeah, I mean, it's pretty awesome, right? And who here has written Flink programs before? Okay, so we kind of have a good sense of TensorFlow. We have a good sense of Flink. That's good. I'm going to start with some background on what TensorFlow is, and then what motivates this project, and I'll show you what we've done so far, and go from there, okay? So as you know, TensorFlow is this hugely exciting platform for machine intelligence. It's based on kind of a simple idea of being a symbolic math library. You give TensorFlow a compiled program that represents a data flow graph or a computation. And TensorFlow executes this on some combination of CPU and GPU on your device. The TensorFlow Core is actually native code, but it's commonly programmed using higher level language bindings, like in Python or Go or Java. And one of the big ideas of TensorFlow is that you can train a machine learning model in one environment and then use that model in some other environment. So for example, you might train an image recognition model in a GPU cluster, and then use that model for inference on a device, like a phone. TensorFlow is being used for all manner of things, and if you haven't seen much of it in action yet, there was a recent TensorFlow summit, and the whole video series is posted on YouTube, and I definitely suggest you consume that. It goes through all of the amazing things people are doing with TensorFlow now. And at least three big scenarios that come up is language understanding, be it your phone understanding your words or your texts, image or video or audio recognition, and even the creative arts. For example, there are TensorFlow models that do like dream imagery and things like that are all like really creative. And another project called Magenta that actually does music composition. So the utility of TensorFlow is really tremendous, but there are using it in Flink is kind of a long-term goal, and I'm going to talk to you about what we might do in both a short term and a long term. But in the short term, a modest goal that this project attempts to address is how could you take a TensorFlow model that was trained in a GPU cluster and use it in a Flink streaming or batch program. What has been making that possible is that the idea of training a model and then exporting it to another device or software environment is become more formalized. The TensorFlow community recently introduced what's called the saved model format. Saved model is kind of an evolution of an ad hoc approach that people have used for a long time, where you export both the so-called graph definition, which represents the symbolic math computation that you want TensorFlow to do, plus whatever state you've learned, like in a neural net, maybe the weights that have been learned, exporting those into a format that can be used elsewhere. With the saved model format, they've taken that a little bit further in 2 or 3 ways. One is that the export process scrubs the model and prepares it for inference. So for example, if your computational graph has got elements that relate to training the model and elements that relate to inference. Exporting the model will simply reduce it to a model that's optimized for inference. Secondly, there is additional typing information that's saved in what's called a metagraph, which describes how the model is intended to be used in other systems. For those who have actually tried TensorFlow, you probably have seen sort of at its heart this notion of running a TensorFlow graph. And when you run, and I'll show more about this in a minute, but when you run the graph, you draw some data through it in sort of one pass. And the set of inputs that you need are what are called the feeds, and the set of outputs that you're trying to get, which we call the fetches, those feeds and fetches have type information in the saved model format. So you know that they're like a two-dimensional tensor of floats or what have you. So altogether, this saved model format is kind of a portable model that you can use in Flink. Now, since I'm going to be talking about the TensorFlow graph a little bit, I'm just going to briefly show a very simple example of what we mean. So if you were to, pardon me. Let's say we had a very simple mathematical expression like this is a regression expression saying Wx, W times x plus b, taking the softmax of that, which turns it into a probability distribution, would be y. This is a classic, softmax regression, one of the kind of hello worlds of TensorFlow. When you write an expression like this in TensorFlow, you're usually writing it in a language like Python, and it's being written in the form that you see here in the second block. This articulates, some mathematical expression, but it doesn't execute it at this time. Instead, it constructs a data flow graph. For squirrels in the room, that's a highly familiar concept, right? Like with Flink programming, in your main method, you are building a data flow, and then it is compiled and sent to a remote cluster for execution. In that same way, in TensorFlow, we use some language or another to articulate the symbolic math we want. That's compiled into an intermediate form that uses protocol buffers. And then that's handed to a C++ core that runs the graph on some CPU and GPU combination. Therefore, one might ask the question, how would you incorporate that into Flink? At least one simple approach would be to think of a TensorFlow graph as being what in this example would be a map function. So if you envision a typical Flink streaming program, can we use a TensorFlow graph as the map function in this particular case, where the inputs into the map function really become input tensors, and the output tensors become the output to the map function. Obviously, it would be nice to be more powerful than just this, but this is kind of the starting point, if you will. So I've kind of talked to you a little bit about what TensorFlow is and why there is kind of a basic, the basic possibility exists to do some kind of integration, at least with respect to inference. There is another insight, if you will, that makes this possible. If you look at a TensorFlow program, the graph that's constructed is executed by the core, but this is a very simple, linear transformation of information from left to right. But in any real training situation, you actually have this in a loop. There's probably some loop that's taking the outputs, which maybe be a a loss computation, and then adjusting weights, and then driving more inputs again and again. So the way TensorFlow is built is it's actually the user code that drives those loops, or that acts as the pump, if you will, driving input data through a TensorFlow graph many, many, many times. All of that logic that has to do with reading input records, driving these various queues of input data through a TensorFlow sort of training system, all of that code is actually in the Python layer. It's not really intrinsic to the TensorFlow core. And so that gives us this possibility that we could run or take advantage of that TensorFlow core in a Flink application and have Flink be the driver. That is kind of the basic insight that this project is founded on. So with that, I'm presenting to you today an open source project that has the modest goal of performing inference using pre-trained models in a Flink streaming program. While it would be great to be able to do the end-to-end training of TensorFlow models in Flink, that's a long-term goal. This is a more sort of immediate thing of using the saved models in particular in Flink. Now, because this is an experimental system, it was built in Scala. I would love to see it support other language bindings, but it happens to be Scala focused right now, though I bet you could probably write a Java Flink program that used this as well. So as I say, this is aimed at using TensorFlow functionality in Flink. This is not to be thought of as a compatibility layer. Like if you were to take a full Python program today, you know, the entire body of the Python program, that's not running on top of Flink. That's not really our goal. The goal is more, how do we take advantage of the TensorFlow core? The way to kind of think about it just simply is, can I use a TensorFlow graph as a map function? That's kind of where it starts. Though, to be clear, it's just as interesting, or maybe more interesting, to use a graph in a window function or other Flink functions. It's not strictly for map, but that's kind of a good mental model. All right. Well, how about we do a demo? I'm going to show you a straightforward demo called Johnny. This is based on an old cyberpunk movie where a certain character has some all-important data stuffed in his head, and it has to be encrypted with a series of picture passwords. And you need to have the original video frames to decode it. Unfortunately, some of the frames are lost, and poor Johnny has to go through some adventure to get them out. In this case, I'll show you a Flink program. In this, you can see it on YouTube if you visit my GitHub site. So in this case, I'll show you a little sample of Johnny as a hypothetical kind of security system, where a Flink program is watching some input stream for a series of images. As each image arrives in the input stream, a TensorFlow model called the Inception Model is used to label the image. If we see the right series of labels corresponding to a series of pictures that we're looking for, access granted. This is kind of fun because it combines the use of a TensorFlow model with other Flink functionality, other libraries, like in this case the Flink Complex Event Processing Library, or CEP library, which is kind of a nifty library for detecting sequences in a stream. Oh, no, that's okay. Thanks. Let me just quickly walk through the example code. It's only one page of code, and then we'll actually run it. What basically will happen is we will create an image stream of input files. In this case, the library has an input image format that can read files from the file system and takes advantage of some built-in Flink functionality that can continuously monitor a directory. And as new files appear in the directory, the input format is given an opportunity to parse that into some type. In this case, the type that emerges is a tensor. It's a four-dimensional tensor that is like a mini batch of photos. In this case, only one photo at a time because I'm using this in kind of a map function kind of way. So given some input image, we use this Inception model, which I'll show you how that's defined in a minute. And then we use that model in a kind of a simple map function. And the body of this map function, no need to dwell, but basically it converts the input image into a tensor, labels the image using the model, and then converts the output tensor to a type that ascribes a label, a text label. That is sufficient. That produces this stream called label stream. Okay, and this stream will basically be saying this image was a caterpillar or this image was a cheeseburger, and then the next part is a little bit of complex event processing that in this case says, I'm expecting a pattern where I first see a cheeseburger with some degree of confidence, then a ladybug, and then a llama. Let me scroll this up a bit. A cheeseburger, ladybug, llama. And you've got 60 seconds. If you can produce that in 60 seconds of event time, you win. All right, let's do this. I'm going to launch this demo application just using Flink Run. I'm asking it to run the Johnny program, and I'm going to be providing the path to the Inception model that I'll show you this content of this directory just after the demonstration. And then the second argument is just a photo directory that we're going to drop photos into. So you can see our streaming Johnny program is running here. And now what I've got to do is put this down because I only have 60 seconds to produce this little string of photos, okay? critical path is done there. I can pick this up. So you can see here in my photos directory, I've dropped those 3 photos in there. And as each photo was picked up, let's just go to the standard out here. Do tell if this is hard to see. Can people see this? No? I heard a no. It's towards the bottom. What you can see here is as each image is processed, I produced some debug output here, and you can see that the TensorFlow Inception Model was able to label the incoming images with some confidence. And these little confidence scores, this is like a probability distribution, and I'm just printing the top 3 probabilities here. This was a 73% chance that was a cheeseburger. That didn't do very well, to be honest. It was a 5% chance it was an orange. And a 5% chance it was a mushroom. So, okay. Now, ladybug, there's an 87% chance that that's a ladybug, a 12% chance it was a leaf beetle. And then the third one, a 65% chance that that was a llama. And could have been an ostrich, it says. A 30% chance. So that was sufficient for the complex event processing module, which picked up these 3 labeled image objects as they passed further down the stream to conclude that someone has given Johnny the right password and he should spill his guts. Not literally, I hope. So let's go back to the materials here, and let's talk a little bit about what this awesome Inception model is. Because if all of this work just allowed you to use the Inception model, I mean, that's kind of cool. This is actually a really cool model, because let me tell you a little bit about how it works. I know with so many hands up in the room, you probably encountered this, but let's just recap how it works. The Inception model is like a deep convolutional net that has gone through a lot of evolution and is kind of represents the best they've found for doing straight image labeling. And it's trained, it's provided as a pre-trained downloadable model. The model files are only 50 megabytes in size. And this 50 megabyte file is really the trained weights of this convolutional neural network. And what it captures is some knowledge, sufficient knowledge to recognize 1,000 unique real-world objects that appear in a particular data set called ImageNet. ImageNet is millions of images containing 1,000 unique labeled objects, like ladybugs, refrigerators, cheeseburgers. What we've done here is simply made use of that knowledge to label incoming images. In terms of the pipeline that we used in Flink then, what happened was we used some kind of connector. Maybe that was from, in this case, the file system, but much more interesting might be like a stream storage system, like what we're showing with Pravega out at the booth. That stream source is assumedly giving you some raw imagery in this case, which I've just labeled as burger.jpg. Then in this demo, we actually use 2 TensorFlow models. One model is simply a JPEG loader, and it loads and normalizes the image into kind of a standard form. And then in the second stage, it's a labeling model that takes that tensor as input and produces some labels. Now, how these labels come out is numeric, right? It just says there's 1,000 possible objects that can be recognized. Object number 1, well, we're 2%. There's a 2% chance that it's image number 1. It was a 97% chance that this is object number 623, which is, a ladybug. TensorFlow has some pretty cool visualization tools. So this is one rendering of the Inception model. It's some deep convolutional net. So for the time that I have left, I'm going to show a little bit about how to use the library and just chat a bit about future directions, and then encourage you hopefully to try it out at home, and maybe we can work together in employing this in your own work and go from there. So there's 3 steps. You have to import this model, and I don't mean copying files around. I mean, we've kind of made an effort to build a typed system around these models that takes advantage of the saved model format. Since, as I mentioned, there's type information or what are called signatures inside the saved model format. So our first step is to define a class that represents this model. The second step is to deal with tensors. So, and I'll talk a little more about that in a second. And then the third thing is, of course, using the model in some kind of Flink program. So to import the model, let me show you, if I can. I want to show you what these save model formats really look like. Excuse the color. Basically, this is not the Inception models but an example one that represents loss functions. They're basically a data structure that says this model has something we call the input, and that's bound to a particular graph node, in this case a placeholder node. And there is some outputs that are bound to some other output nodes in the graph. And as a whole, this is, you label it with what's called a method name. So this would be considered the standard form of the compute loss method. So it's an interesting little question of how would we in something like Java or Scala represent this compute loss method such that you could work with this in a typed way. Now, we've tried to do a little bit of that, but I must say that it's not very satisfying right now, and I'd love to figure out a better way. But there's really 2 parts at least. One is building a class. In this case, this happens to be an MNIST model that extends some base trait called the TensorFlow model. And this you use if you have a proper saved model format. There are other model subclasses here you can use to work with the more ad hoc TensorFlow graphs. So you basically expose some set of methods on your model class, and then by using some of the helper functionality that's there, it takes care of the heavy lifting of loading these models and dealing with things. And then this other part at the top is something that tries to articulate what is the types of the inputs and outputs. And the main goal here is to support conversion with implicit converters, so that, say you have an array of floats, there are some converters provided with the library that can convert that into a tensor. Now, I want to say a little bit about tensors. Tensors are multidimensional arrays in TensorFlow, and they are unmanaged objects, right? They're large unmanaged buffers that are being allocated by the TensorFlow Core. But the Java language binding supports byte buffers. So if you've got both direct and on-heap buffers, so you can kind of, excuse me, you can relatively easily take arrays of the various primitive types and wrap them in a byte buffer and then hand them to TensorFlow. What you're doing there is allocating a lot of unmanaged memory. And so you probably want to adjust your Flink's cluster settings so that you allocate. There's a ratio setting in Flink that says how much of the overall container memory should be allocated to the Java heap versus left for somebody else. And you've maybe seen in other talks that there's special, you dial that a certain way for using RocksDB backend. Well, you should also dial that if you're expecting to do a bunch of unmanaged memory allocation through TensorFlow. So yeah, you've got the, large tensors allocated, but they're closable, so you have to take care of them. They're not going to live very long. They're going to live within the context of your map function in all likelihood, or your window function, maybe when you're dealing with a batch of inputs. We've tried to find different ways to help you with that, and one way is to use Scala's resource management library, which is called Scala ARM. When you deal with auto-closables in Java, that's where you use the try with resources idiom, right? So that you open up input stream and it closes automatically when the little try block ends. Scala doesn't have try with resources idiom, but it does have this ARM library. And so we've been kind of playing with different ways of using that to manage the life cycle of the input and output tensors that are flowing through TensorFlow. I think it's really interesting to not just use a TensorFlow model in a map function. I think it's really interesting to use it in a window function, especially since that could give you like a batch worth of information to process in a single interaction with TensorFlow, which makes a lot of sense if you're using GPUs. Since if you invoke TensorFlow sort of on an element-wise basis, it probably won't work well because of the nature of things. Another way that I think is really exciting is with process function. Process function is an evolution of the map function in Flink that gives you timers. And for those who did the advanced training yesterday, they have a really cool walkthrough of doing that, right? So I get really excited about the potential of using event time in a first-class way with machine learning models. So many models now are sequence-based, right? But it's even better if you could, use the absence of an element, like a timeout, to actually, end a logical sequence. Like, for example, an RNN that's doing language processing, if there's a large gap, where there's no new input, that maybe indicates that the speaker is done speaking. So event time and machine learning, I think, have a really interesting future. And so this is, being able to use these things in a process function is kind of a way to experiment with that. There's just one little caveat you've got to pay attention to when doing this. The model has a life cycle. My next slide will talk a little more about the runtime, but basically you need your function to be a model-aware function, which means that the function opens the model and closes the model when the corresponding when the Flink function opens and closes. What you typically get with the rich function interface. It's important that that is connected to the model piece, because the models, we want to open them when your function opens and close them when your function closes. And so to make that a little bit more clear, this is the TensorFlow Core running in the task manager process. Right? This is not the distributed TensorFlow, and this is not running TensorFlow installed separately on your machine. This actually all just works inside the Flink cluster just by virtue of submitting the job. That's really awesome. But in terms of how many TensorFlow graphs and sessions are actually instantiated, the short answer is that you get one model instance per subtask. So if you were to have a map function that had a high degree of parallelism, you would have an instance of the TensorFlow model instantiated for each subtask of that operator. Right. I think the potential in the future is really great, but I frankly don't know where this will go, but I would love to begin to work with stateful models, right? And to do that, in other words, going beyond inference, where essentially the TensorFlow model is stateless and is just producing some inference with a pre-canned model, could we actually have a stateful TensorFlow model? And what that would mean is that as you invoke the TensorFlow graph, you might be mutating some of the TensorFlow variables that are stored in that session. The big question is, can we join that state with Flink's checkpoint state so that the overall state of the system evolves together? I think there's a real potential to do that based on how TensorFlow manages state under the hood and some of the low-level checkpointing functionality of TensorFlow, which can be, I think, integrated with Flink, but it will require a lot more investigation. The main reason why it's not easy to just pick up and do new TensorFlow models from scratch in Flink today is because there's no graph builder DSL today. I just want to make that clear that the Java language binding of TensorFlow doesn't really provide that full range of that full DSL that you use in TensorFlow Python to build new graphs. You know, when I showed that little code snippet at the beginning, it showed a series of Python statements that were defining a variable and then using some functions. That stuff is all Python code that is ultimately producing one of these graphs that then runs in the TensorFlow Core. There's a lot of Python code there to do that. And while the Python community is very keen on supporting other language bindings, Python remains the only real, fleshed out language binding for graph construction. So that's why in the short run, we have to emphasize building your graphs in a Python environment, training them, and then using them here in a Flink environment. There's other fun things to do. There's some really cool instrumentation support in both TensorFlow and in Flink. So TensorFlow has what are called summaries, which causes it to dump out some telemetry that can be consumed by another tool called TensorBoard. We can poke TensorFlow graphs even from the Java binding in such the way that some of that summary data does emerge. So I think integration with TensorBoard would be a kind of a low-hanging fruit and be really, really cool. And the second thing is Flink metrics. You know, there's lots you can do to instrument your Flink programs and functions today, and that should be done here too. And then we have to get into model versioning, how to ultimately upgrade models, and that should be done, I think, in combination with Flink's versioning strategy, save points, and the like, so that you get a kind of a consistent system. So, thanks again for your time today, and this is just sort of the beginning of an ongoing effort to make use of TensorFlow in Flink. I'm really excited about the potential, but I think there's something you can use here today. If you see a TensorFlow model that you want to use for inference, I think this library can help you. And so thanks again for your time. I'm happy to take questions.
Are you able to use GPU TensorFlow on the task manager instances that are actually running the model?
I don't know of any reason why not, but you'd have to work a little bit harder with you have to build TensorFlow from source, among other things. So it's kind of a thing that I believe can be done, but I haven't succeeded in doing it.
So is this a replacement task manager at the moment? Is that kind of how that's linked in with TensorFlow, or is it part of the job? Is it part of your jar you submit?
Yeah, it's all the TensorFlow dependencies are encapsulated in the job jar. Okay. And that's because the TensorFlow Java binding actually has native libraries built into its jar file that unpack when you instantiate TensorFlow. But those are CPU builds. That's why the GPU piece doesn't work.
Like how much memory does your embedded the tensor core, the core takes, and any issues on like have it long running, like any kind of memory leak or kind of those kind of issues?
There's two ways in which objects are allocated here. One is the graph itself in what's called the TensorFlow session, and that is really tied to the life cycle of your rich function. So where your function opens and closes, after it closes, there should be no enduring TensorFlow usage. But the other thing is tensors themselves, and that's why it's important to use ARM or something like that to make sure you're closing those input tensors after you kind of drive them through the graph. Hi.
Did I understand correctly that you're loading the model for every map and then?
Yes.
Yes.
The rationale for, as opposed to loading a model that could be shared by many functions, the rationale is that the state of the graph should be really become managed Flink state, and that's done on a per operator basis in Flink, and so it's I anyways think of it as the entire graph is actually a part of the function state or operator state. No, not every invocation. When the rich function opens, the model opens, and from there it's a call to session.run in TensorFlow speak. Thank you. Thanks again.